Okay, so thanks for that. Let me see if I get all this right. Hold on. Okay, so that's my title slide. So I was here last year in March, and I found it such a nice place I decided to come back. And I have to tell you this much, and I don't lie. I'm known to be a person who tells it straight. This is one of the nicest cities I've ever been in during the summer. I suspect that during the winter you're all taking so many antidepressants or whatever that you keep taking them during the summer, and then you're all very happy. But the people here are incredibly nice. So my wife just went back to Ireland yesterday for a while, so we both enjoyed it very much, so thank you for that. So like I said, I was here last year, and this is evidence. We have a picture there with me and some usual suspects, so to speak. And the theme was the good, the bad, and the ugly. And I was thinking to myself, how would I pick up from that? So I looked and decided, well, maybe, I'll have this one. The good, the bad, the ugly, and maybe it says I'll be back. However, I decided to look at the conclusions from last year. This is March 8th, 2016. They're the conclusions. I'm not going to go through them in any detail. I'm a great man for using Google. I don't know, Google is useful for some things, but it's particularly useful for if you want a picture for a slide. You just put in some words and you get something useful. I actually put in, that these conclusions still hold, so I said change your mind. But unfortunately, everything up there is all about if you never change your mind, why have one? If you can change your mind, then you're not using it. So unfortunately, my plan backfired on me. I thought I'd find something relevant. But being a good scientist, these were the findings. That's what I put up there. I did have a picture of a certain gentleman from down south who changed his mind a lot, but I decided that would not be appropriate. So in red there is the sort of the follow-on, if you want, from last year's talk. Last year's talk had these conclusions, and this was one of the conclusions, and I'm going to pick up from there. However, being a man of habit and not changing things, I decided I'd go back to Clint Eastwood, but I decided I would update him a bit and bring him in, because we're looking much more to the future. So this is Dirty Harry. Yeah, it's a pretty good movie too, not as good as The Good, Bad, and the Ugly, but I decided I'd use him instead. So it was a compromise. So the theme of this is, does Quebec feel lucky? Okay, and that is the theme, because I was asked to sort of talk and bring Quebec into it. So we'll see how we go, and well, I suppose you'll all have the, well, do you, punk, and that's the catchphrase in the end. So we'll see if Quebec feels lucky. Also, just to be clear, if people wish to, if people wish to ask questions as I go, please do. That's the way I like it. Maybe that's not the way Tyson likes it, but that's the way I like it. So if anyone wants to ask a question during, please do. And I won't shoot you, I promise. So let's start from home. I decided, because being the Irish Canadian University Foundation Flaherty visiting, it's a long title. I decided that there's a bit of sort of, it's not only about being an academic engineer, but it's also about building bridges between countries, etc. So I decided to look at, my linkages to Canada. So I started off in the top left-hand corner. So the first ever transatlantic cable was between a place called Valentia and Newfoundland, okay? So the first thing about that is that my wife's sister lives 4 miles from where the cable landed, okay? So that's the first linkage. That's a piece of the cable. But much more importantly, on the bottom right-hand corner is a man called Halpin. He's on a stamp there in Ireland, 48-cent stamp. He was the man who captained the Great Eastern, that put down the cable that continued for many years. There was one a few years beforehand, but it failed. And he was the captain of the Great Eastern when he put it down. On the left-hand side of the bottom is the house he built in Wicklow, which is about 30 kilometers south of where I live. That is now a hotel run by my sister-in-law. So I'm very much related. And this is actually the Milestone event. One of my last sabbaticals in the US, I organized a Milestone event because it's a very historical place, IEEE Milestone 2001. There's the picture. Now, I don't have a laser pointer, but I think this gentleman here is actually the husband of my sister-in-law. This is a man called Wally Reid, who's from Newfoundland, who was the president of the IEEE Power Engineering Society. I don't know, Francois, did you ever know him? Before your time. So him and me did it. So this was the event. This man here is actually an Irish politician, and he wears a hat. He's, I won't say anything about him. This is me when I had hair that wasn't grey. And this actually is, I don't know, you have ice hockey here, we have Gaelic football. This is the most famous Gaelic football player of all time, a man called Mick O'Connell. He was the best Gaelic football player that ever lived. And that's one of our ministers, and that's a Canadian representative. So we get on from that anyway. That's the sort of the nice bits done. So I'm well connected to Newfoundland. I don't know about Quebec. So if you look at Ireland, this is wind installed in Ireland. I've shown this slide many times before. It shows the wind we've increasing amounts of wind installed. And I tried to get an update of the percentage of electricity from wind 2016. It's actually lower than it was in 2015. The reason is, because when somebody gave me the number, I said, no, that's wrong, because in the previous slides I had 22.8% in 2015. I said, how could it be lower? It was actually lower, because 2016 was a low wind year. And in fact, our load growth, we're having an economic boom again. So strong load growth, and wind is variable, as we know. And in fact, so a low wind year and strong load growth mean that the percentage penetration is actually less in 2016, even though there's more wind installed. But the point is, if you look, if you go to this URL, it's EirGrid. EirGrid is the transmission system operator in Ireland. The CEO is one of my students. And they have this smart grid dashboard, and you can track the wind, the load, etc. So this is the 29th, it's a few days ago, and you can see in yellow is the system demand. Oh, sorry. The yellow is system generation, which is slightly different than system demand, because if you look at the top, we're exporting to the UK. In fact, we've so much wind on our system now. We previously, for economic reasons, we were a net importer from the UK. We're now a net exporter to the UK because of the amount of wind we have. So generally speaking, we're exporting. So the total system generation there, this number plus this number is over 100 because it's made up with this net export. But you can see at the time, and this was some time in the evening time, I don't know what time it was, see how late I work, look? I tend to work very late. You can see that the total amount of wind was nearly 50% out of 107, which is not quite 50%. But you can see there's an awful lot of wind, and during the day there's an awful lot of wind. I tried to get a day that was closer, but the wind in the last couple of days has actually been very small in Ireland. If you look at it over a monthly basis, this is it. So the yellow is system generation, and the blue is wind. And again, you know, some of it's been exported, I would say. But the point of this slide is to pick up where I was last year, is that if you want to meet supply and demand on a system with lots and lots of wind, the wind has a tendency to be variable and difficult to predict, etc. And therefore, what you end up is this situation here. So this is a slide by my friend Michael Milligan from NREL. And as you can see, so this is the load. The red is the load profile of a normal load. The green is the wind. If you have a resource like wind, the expense is in the capital that you spent on it, so you'll try and take the energy if at all possible. And if you try and do that, the blue line essentially becomes what you have to meet with the rest of the generation. And as you can see, it's much more, it's got steeper ramps, it goes down and up much faster, and it goes down further and deeper. Therefore, you need flexible plant to balance it, okay? If you did solar, solar is somewhat similar. Solar and wind are very similar in many respects of nearly everything I'm going to say, but there are differences, but I'll concentrate mainly on wind. So if you do that, but you then go and look at our April 2017 fuel mix, and actually April would be a pretty good month for wind usually, but you can see here, this is a monthly average, and you see that wind, renewable 16.63% is almost all wind, not quite, but nearly all wind. So it's actually quite a low wind month was April. But if you go back to January or December 2016, we had 43% of all electricity was generated by wind. But the point of this slide is not the wind, it's the red one, it's gas. So what we have in our system to manage supply and demand is gas, okay? And the thing about gas is, gas grids have storage. I mean, I've shown a picture here. You can store gas very easily. The pipes themselves have gas. I think this is from Alaska. I'm not sure, but I'm sure it's somewhere there. But, you know, gas itself, by its very nature, you can store it. Even the pipelines have natural storage in them, etc. So gas is a very good fuel to match variable renewables. I'll come on to talk about Quebec, because Quebec you have hydro, which is not that variable. But the point of this slide is to show you that electricity and gas are linked. We couldn't integrate all the wind we have on the electricity system unless we had a good gas network, and we have plenty of gas to meet it. The other point of this slide is in the bottom right-hand side. That's a jet engine. Does anyone want to tell me if it's a Rolls-Royce or other? And does anyone know the difference? Sorry? But yeah, I know that, but which one is that? That's only half the information. Anyway, he's right. Huh? Rolls-Royce, yeah. Apparently Rolls-Royce patented to turn in one direction, and everyone else, to avoid the patent, had to make it rotate in the other direction, which is interesting. And I have no idea which it is, so thank you for that, because I have no idea. Anyway, the point about it is that gas generation effectively is a gas turbine. Effectively, it's the same as a jet engine. And jet engines are incredibly easy to start, stop, etc. And gas generation is very flexible. So that brings me on to the sort of the launch pad for what the rest I'm going to say. So this is the whole area of energy systems integration, which I mentioned the last time I was here, but now I'll deal with it in more detail. I showed this diagram before. So this diagram was generated by the National Renewable Energy Lab in the US. And what it shows you, I'll just get this, yeah, here we go. It shows you all the energy vectors: electricity, thermal, that's heat and cold, fuels, and it also shows you water, data, and transport, and it shows you the different dimensions. And the idea of energy system integration, the whole concept, and it comes about because if you try and integrate lots of renewables on systems, what you find is you can't just integrate them within the electricity system or within your country or region. You have to start expanding out. It brings up the, I suppose, presidents of the United States are pretty topical. Andrew Jackson apparently was a topic of conversation yesterday, but I think it's a man called Eisenhower. So Eisenhower wasn't a particularly good president apparently, but Eisenhower is saying that if a problem gets difficult, if you expand it, the solution emerges. So that's the concept that we're on here. If you try to integrate enormous amounts of variable renewables, wind and solar, onto systems, you find that you have to make the system bigger to absorb it, or you find you have to use the gas system to absorb it, or you find that you have to dump the excess energy, electricity, into heat or transport. And that's the whole concept, and it's come about because of that. So what the diagram here is trying to show you is that across the dimensions between the consumer and the region, the connections are becoming tighter, and between electricity, heat, and fuels, it's becoming tighter as well. And also, water, data, and transport. Transport is a network, but it uses energy, obviously. Data is a very important enabler of the whole thing. And water is a special case because it is, we're not going to talk about it today, but water is a very, very important. In fact, the world will face a water crisis before it faces an energy crisis. But water is very important because it's a huge enabler of energy, and it's also a huge consumer of energy. So the bullet points there, it's optimization of the energy system across multiple pathways and scales, increase reliability, performance, to do it and minimize costs, to reduce emissions, etc. You have to do it for some reason. But the place that we're really interested in from a scientific point of view at the interfaces where the coupling is strong and there's opportunities or there's challenges. So in other words, if there's a coupling between the energy vectors, or if there's a coupling across space where there's a problem, then you have to address it, or if there's a coupling where there's an advantage, you should use it. And that's essentially, so therefore it is quite focused. But the most important point from this talk is the control variables. It's not just engineering, it's engineering, economic, regulatory, and anthropological. Now, I don't know if I've used that word correctly, so bear with me, because it's the first time I've used it. But I did meet one recently. But just on the theme of saying that, that gas helps the Irish system to balance wind, you then have to look and say what negative impacts it has, and that's very important. You're not just looking at where they interact in a positive way, looking at the impact in a negative way. So obviously, if you're trying to balance wind on a system and the gas units are doing it, and you got lots more wind or solar, you'll find that these gas generations are going up and down, turning on and off more often, etc. So we did some work, and I'm not going to go into, I'm going to show slides, the references are at the bottom for the details. But this is trying to quantify the amount of the impact that increasing wind generation has on the ramping of gas plants and also on the number of shutdowns and turn-ons, etc. And it's trying to calculate the cycling impact. And it does have an impact. There are costs associated with this. And there's lots of people who have worked in this area. And I'll leave it to you to follow up on the references. But my point is that it's not just, so when two things interact, it's not always good. Sometimes they're bad things and you must quantify them. So that should illustrate that. So I did meet an anthropologist recently. She's from McGill University. Her name is Gretchen Back, and this is her book, The Grid. So I think I'll start off there. So defecting consumers, because we're not only talking about engineering, economics, regulatory, we're also talking about human beings and what they do. And this is where I get into real trouble because of terminology. So I'm an engineer, let me use my terminology, I could be wrong. But anyway, going off the grid is a big issue now. I don't know if it's a lot of talk about it, certainly around the world. This is I stole this from somewhere on the internet. It shows it to you pretty simply. Basically, it's saying that people can, because they can buy PV. Now, why someone put a wind turbine in their home, I have no idea, because the economics make absolutely no sense at all. PV makes very little sense in some places, but wind at small scale makes no sense because it's It's a cube law, essentially, a square law. So really big makes a lot of sense. PV is a little bit more sensible because it's surface area. So, but anyway, this is what they put in, and they're saying we'll go off the grid. So this diagram comes from Germany, and it comes from a good source, German Trade and Investment, and it shows you, if you can see it, it's got 3 graphs there. One shows you let's see this, yeah. One shows you, this is the cost, the price of electricity, okay, for the consumer. Now note, it's 30 euro cents, which is around 40 Canadian cents approximately. And you're currently paying 7. So this is, okay, 6. I'm here trying to be nice to you people. Anyway, it's 6 or 7 times what you pay here. Is that okay? So that's the first point. Electricity in Germany is much more expensive. The 2 other lines show you, electricity costs for PV. But look at this one here. This is the electricity cost. This is the combined electricity cost for PV and battery. And the point of this graph is it says, hey, look, in 2017, right now, there'll come a point where, in fact, buying PV and a battery is cheaper than buying it off the grid. That's what the graph says. Correct? No, not correct. This is a classic case of, I can't resist it. This is a classic case of, what do they call them? What does he call them? No, I'm talking about the gentleman in the south. What does he call it? Yeah, it's a classic case of that. You said it, not me. You've got to dig into this. So first of all, the price of electricity does not just include the energy price, because that price of electricity in Germany includes the cost of the subsidies for everyone who bought PV and the batteries. So in fact, in that price are taxes, levies, there's the subsidy price of the PV that not only that you're putting on your roof, but that was put on someone else's roof 10 years ago. So it's all bundled in there. So in fact, that price of electricity is not actually really, you can't compare them. It's not possible to compare them. And in fact, all this is a very elaborate tax avoidance scheme. That's all it is. And what's going on in Germany at the moment is that people are putting PV and buying batteries, and all it is the PV and batteries are being subsidized by your neighbors, so that's great. And you are managing to avoid this enormous price of electricity in the black, because in it has the cost of energy, the network, but also has the cost of the taxes, the levies, and the subsidies for all the previous PVs put in. So all this is a tax avoidance scheme. And interestingly enough, it only favors the rich, because the rich are the only people who have money to invest in the PV and the battery to start with. So it's not actually true, it's completely false. Totally and absolutely false, makes no sense. Now, if it makes no sense in Germany after what I just explained, how much sense would it make here when it's the fundamental price is still 1/6, yeah? The answer is virtually none. And also, I think Germany and you guys about the same. You're further north in Germany, are you? You're both in good, poorish enough some places, I would suspect. But this brings up the spiral of debt that people are speaking about. So what's going on, people are talking about this, and what's going on is that because of these, and all these things, if you go to any system in the world, the reason that people are putting PV and batteries on their houses, largely speaking, almost always is because of perverse incentives, because of the tariffs, etc. It's very rare that it actually makes sense. But sorry, it makes sense to the individual, but it may not make sense. So what's going on, if you go up here, you start off here, people put solar on the roof, the utility sells less power, but they still have a lot of fixed costs, because the fixed cost of the utilities are generally bundled into the volume. So if you use volume, part of the volume charge you're paying for the network. What that means is the utility has to hike its prices because it's got fixed costs. That means that solar becomes more attractive. That means more people do it, and the whole thing spirals to death. This idea that somehow the utilities are going to die is absolute nonsense, because this is just a complete and utter perversion and has to stop at some stage when sense prevails. And to say that you can get rid of the utilities is just nonsense, because it's incredibly expensive to go off the grid. So this is numbers, and again, the Grattan Institute, they're okay as far as I know. I asked an Australian recently, he thought they were pretty good, so I'll take these as reasonable numbers. This is Australia, and remember, Australia would have sun, yeah? So that's a first up for Australia. But mind you, Australia would have enormous electricity prices. Last week we were discussing it, they're around about 5 times what they are here. So they're not as bad as Germany, but they're 5 times. And the reason seems to be that they've put an enormous amount of investment in their network recently. And the other reason behind it is that the distances in Australia are absolutely enormous, and therefore the network charges are very high. Anyway, they pay quite a lot. So this is some work done by the Grattan Institute, and it shows you that if you want to go off the grid, these are the costs. But it depends on what level of reliability you want. This level of reliability, 95%, is not what you have. You have more like 99.9% reliability. And therefore, the cost is approximately 6 times. So to provide electricity in Sydney is by going off the grid, is roughly 6 times more expensive than taking it from the grid. The important point is that you maintain the same level of reliability. So it's very expensive. And there you go. I don't have to put this in front of you. Residential electricity rates across North America, you are the cheapest. Apparently Manitoba is second cheapest, but you're the cheapest. You're the cheapest electricity prices that I found in the world. I think South Africa might be cheaper than you, but I'm not sure. But look, you're getting it pretty easy. So then if you go and you say, if you look at flexibility, flexibility is the concept that, supply and demand has to be balanced. This is some work done by Juha Kiviluma, who works partly with me and mainly with VTT. And he looked at demand response, batteries. He looked at heat storage, heat pumps, which I'll talk about further. So this is the whole concept of this down here is electricity and heat been interacting with each other, battery EVs. So this is the whole concept that if you're trying to get flexibility, you get it from other parts of the energy system. You use EVs, you use heat, you use transport, etc. And if you look at it, he does some numbers here. He did a study for the whole of North Europe, with no transmission in it. So he has an aggregation that levels all this out. Can you imagine? And he came up with, that's G euros, that's billions of euros, okay? So you're coming up with numbers there of several billion. Can you imagine if everybody had to balance their own system? Because then the aggregation issue would go away. This number would probably explode into, 300, 400, 500 billion. It would be exponential. So in fact, this whole idea that you can make a system smaller and somehow balance it very easily is not actually correct. And that shows you there. There's solar PV aggregated over 23 sites and aggregated over 1 site. The variability is so much. So by adding things together in a bigger system, you get rid of the variability, you get rid of the need for flexibility, you reduce costs. So this idea of going off grid simply makes no sense at all. And in fact here makes absolutely no sense. And furthermore, I'll skip this slide in order for time, but if you do metrics on it, we do metrics to measure flexibility. I'm sure if we did this metric for measuring flexibility of an individual off the grid, this is insufficient ramp rate expectation. It's coming up at 1200 there. I would suspect for an individual with PV in the roof, our insufficient ramp rate expectation might be the order of 120,000 as opposed to 1,200. So people talk about the trilemma. They talk about, the trilemma is the classic case of economy, environment, and security of supply. And here he is here. This is otherwise known as the President of the United States, apparently now, according to a comedian in Washington, D.C. I didn't say it. Anyway, to be honest with you, I think the trilemma is not... Actually, I went to look for it. There is a word called quadrilemma, believe it or not. I didn't think there was. So I don't believe there's a trilemma or being there's a quadrilemma, because I think the consumer or what the people want to do, because people will go off the grid, don't get me wrong. I'm not saying everyone rationally looks at it like I do. They're going to do it. And they're going to do it. Lots of them are going to do it. And therefore you have to take account for them. And in fact, in many ways, what we have to do is design the energy system so their desires are met or halfway between the economic and engineering sense of some description. So going off grid, though, if you just take going off grid as a concept, the minute you go off grid, one of the things that highlights itself immediately, and this is the only time I mention CHP, all of a sudden combined heat and power makes a lot of sense, because you need heating as well and you need electricity. So, and you say, well, and PV doesn't shine at night, etc. So you suddenly say, well, maybe I'll have a combined heat and power in my factory or my campus or my house or whatever. And combined heat and power is very efficient. And so there's a lot of attention to CHP in microgrids. And this is a slide I got from a gentleman who was here last week, Andrew Melchers. However, this slide comes from a project in Ontario, not in Quebec, because I see this making no sense at all in Quebec for the reasons I just said. So I got this report from Francois. This is the 2030 Energy Quebec report. In some ways I should have read it cover to cover, but I didn't. I deliberately didn't. Not that I was out having fun in your city or like that, but I deliberately didn't do it because I didn't want to be perverted by it in any way. So I did dip in and out of it to steal some graphs though. So if you look at it, there's a very interesting section, so I've got integration is not only physical but institutional. And so I think the report's quite good from the little I looked at it. So ensure integrated governance. So in fact, I'm not just talking about physical integration. You have to have, the government, the federal government. Is that what you call them? Federal government? Is that what you call them? Justin Trudeau runs the federal government. Okay. Federal government, provincial government. I'm sure you have a municipal government. Okay, right. You have all that. But anyway, you have to have, these things all working together and all the arms of the state and all the institutions working together. So I think that's very good, and that's key. So it's not just about integrating things physically, but institutionally. If you want an example of how it can go badly wrong, this is an article written by William Dasley and some colleagues in an issue of the IEEE Power and Energy magazine that I was the editor on. And he drew this diagram up. Basically what's happened in Europe at the moment is that, look, what it looks like is wind and PV are pushing coal and combined cycle gas turbines off the system, okay? What you'd like it to do is for CCGT to be the other side of coal. You'd rather push coal out than gas, because coal is much more carbon intensive. But I won't go into in detail, read this article, because the policymakers, the polite word to say is they screwed up. There's other words you could use. They made a complete mess of it. Basically what's happened in Europe is that gas plants are closing and coal plants are being built. And it's all because the policies were not thought through at an integrated European level, and nor at a level of where they interact with each other. So this whole idea of integration is not just about physics, but it's also about policy. I also took this out of the report. You're very lucky here. You have 47.6% of your energy needs are renewable. It's mainly hydro, but also you have lots of trees, obviously. I presume that's where the biomass comes from. And you're going to increase it to 60.9%. I can see nowhere. So you're a huge renewable energy. So Quebec has a huge amount of renewable energy. If you compare it, Norway and Quebec are very similar. This shows hydroelectricity in the world, with Norway being number 1. Canada is number 4, but Quebec, I couldn't find one that had just Quebec by itself. They're basically neck and neck. 98 point something percent in both cases in electricity comes from hydro. So you're very similar to them. Iceland is a very interesting country as well, because it's got a lot of hydro, but also has this slice here which is geothermal. And New Zealand will be similar as well. So Norway. And just from a Norwegian point of view, I'm the godfather to a child who lives there, because my brother lives in Norway. Got to keep it in the family, as the man down south keeps saying. Hydro as well is incredibly flexible. So I put this in. This is the slinky digital flexibility. This is a gas turbine. If you look at hydro generation, it's incredibly flexible. So to integrate more variable renewables on this system in Quebec at a very fundamental level is very simple. Now, I'm not saying it's not difficult. I see my friend here from Hydro-Quebec. There are issues, but nonetheless, at a fundamental level, it's pretty straightforward, because, at least from a flexibility point of view. There are other issues, though, as well, but this is not the place to go into. So transport is the one thing. Sorry, I've skipped over heat, because it's pretty simple. You heat with electricity here, and that's it, and that's a good thing to do. Transport, I think, is the key issue for you guys. In the report, it says you're going to have lots of EVs. I did discuss this with some people. I just went and got this. If you Google Quebec density of or Canada density of population, this is what you get. And very nice of them. They've actually taken this little slide out here and put it up here for me, so it's perfect. You can see that between Toronto and Quebec City, or along that corridor, huge density of population. The rest got nobody living in it. Seems pretty obvious to me that high-speed rail links up and down this corridor make a lot of sense, but that's just me. So I should have talked to you beforehand for the bribe. If I had known beforehand, and anyway, you can give. I suppose my bribe is only half what it is, after the fact. But anyway, I mainly do electricity and heat and fuels. Transport is not an area I spend a lot of time on, but I would suspect that high-speed rail would seem to make sense up and down that corridor. So let's talk about heat and integrating the consumer. And I'm doing this because your heat is already electricity, but some people are looking at electrifying their heat to decarbonize it. So you've already done it. I'm showing you what other people are doing, and there's probably some similarities, etc. So just some work that we've done. So if you take this electricity, heat, consumer all together, and you have to put weather in there as well, you have to do integrated planning. Because we plan electricity systems. Typically, you plan electricity system somewhat in isolation, and you plan all these systems in isolation. But if they're all starting to come together and start to linking, you have to plan them together. The reason why you have to do, so electricity and heat, if you're going to electrify heat, you have to plan the two systems together. Weather is important because if you have an enormous amount of variable renewables in the system, the heating requirement and the wind are probably correlated, and the sun, etc. So weather is now linking them together by the fact that you not only have on the supply side, you have wind or solar providing the energy from a renewables point of view, but on the demand side, you have the heat requirement or the cooling requirement been driven by the weather as well. So the weather is important to look at. And the consumer I've mentioned several times. So integrated electricity planning. So this is a very nice graph. Actually, sorry, I should have put, I'm very diligent at putting the names of the people who I get the slides from in the bottom left-hand corner, but in this one I didn't. So this is one of my PhD students, but he found this somewhere. So consumer satisfaction at the heart of, so people have talked about demand-side flexibility. This is the idea that we can vary people's demand, etc. The key to it, though, is, is consumer satisfaction. You cannot go and mess with their load if they're then dissatisfied. That doesn't make any sense. So, this diagram shows it very nicely. So if you take that into account, and if you look, so this is work by one of my another PhD student I have, Steve Heinen. In the blue, right? Sorry, let me get this here. Okay, blue is electricity. This is space heating, and this is water heating. Now, to say at the moment in Ireland, most of our heating comes from gas. It's not actually electric heating. There is some, but not a lot. About 200,000, 300,000 people out of 4.5 million have it, so it's quite small. But if you want to decarbonize heat, one of the things you've got to do is electrify it. So I think, as far as I know, the brown curves are essentially showing the heat demand for 1/4 of our population, approximately, if we were to electrify it. It's interesting that we do not need any heat during the summer. We still need water to be heated during the summer, obviously, okay? And obviously this will be different in different countries, etc. But nonetheless, the simple fact of the matter is, the key point of this is the following. If that is the demand for heat of 1/4 of our heating, yeah, and this is our total electricity, if we were to electrify it all our heat, yeah, you're going to get a situation where the peak demand for electricity in the winter is going to be, what, at least twice what it is now, maybe 3 times what it is now. So you get this capacity issue. You get this issue whereby at peak winter evenings, you have an enormous demand for electricity, both for the usual uses, but an even bigger demand for electricity as heat. And therefore you get a situation where you don't have enough transmission, you don't have enough generation, and you've got a capacity issue. And apparently Quebec have something similar, not as dramatic as I just described. So the question we asked was, well, how would you address that? Because if you look at these, it's not a great picture, but it'll do. These are smart thermoelectric storage heaters in people's homes. When I say they're smart, they are internet enabled, basically. That's what I mean by smart. They are thermoelectric storage heaters, so they actually they're storage heaters. So in fact, what you can do is, on this graph here, it shows you on a seasonal basis that you have a problem, yeah? Yeah? But if you go into it on a daily basis and say, look, I'll heat during the night rather than during the day, you can shift the peak. So it doesn't show it here, but you can shift the peak. And if you shift the peak, you can get a situation whereby you don't have to build as much capacity. And therefore, you can make an enormous saving. Because, literally, if you look at this, Gordon Strabak has got numbers on this. I think he says that the UK needs to electrify its heat, needs 2.5 or 3 times the amount of transmission and generation as it currently has. Okay? So if you do that, one of the questions then is, so we did a study, and I'm not going to go into this in a huge amount of detail. If you do the study, this shows you if you look at this graph, it shows you that the heat requirement is the heat that is given. It shows you the load, etc. It shows you the storage. If you look at it in terms of this graph here, shows you the loss of load probability and the system marginal price. It shows you, because remember, if you're operating this system optimally, you'll be doing a short-term optimization, which means that you'll be shifting electricity from high price to low price, okay? Because we don't shift electricity on the basis of high reliability to low reliability, at least not yet. And if you look at that graph there, this one down here, it shows you that, the high price electricity, yeah, a lot of them have periods, or do occur at periods of low reliability, but a lot of them don't. So in fact, there's not direct correlation between price and reliability. And therefore, if you're going to optimize this, it has to be done on the basis of basic economics. So this is classic economics, right? The reliability is not coming into it at all. And you end up with a situation whereby the so-called capacity value of the demand side. Now let me explain what the capacity value is. If I put a generator onto a system, a 100 megawatt generator in the system, and I tell you its capacity value is 95%, it means that I can put 95 megawatts of load across every hour of the entire year and maintain the same level of reliability. Because if you put extra load in the system, you reduce the reliability, but if I put a generator that maintains it, its capacity value is equal to the total amount of load I can add at every hour and maintain the level of reliability. So capacity values are always less than 100%. They have to be, because generators, are out in maintenance or they break down, etc. Okay? Just to give you the numbers, wind has lowish capacity values because it may not be that well correlated with the load. But anyway, if you look at the capacity value of this demand side resource, you can see down here, it's of the order of 9 to 26%. There's two different cases in there. Again, in order for time, I won't go into details, there's two different cases. But it's not as large as people would think. People would think, surely you can move the heat demand away from the peak and get an enormous capacity value. The problem is first of all, the consumer has a heating requirement that must be met. Yeah? Number two, this unit here is not big enough from a storage point of view. The storage unit is not actually big enough. Sometimes you need a bigger one. But has anyone ever seen, you have electric, do you have electric storage heaters here? No, you don't need it because you got, yeah. That's the thing about Quebec, you just don't need it, just, it's just free. But storage heaters, if you try and make them bigger storage devices, I'll take a question about bigger storage devices, it means they get physically bigger. They're already pretty cumbersome. But if someone told you get a new electric storage heater in your house and you have to build an extra room to put it in, you're not going to do it. So the consumer has requirements that need to be met, and the size is not that big. And also, basic economics indicates that reliability and price are not always the same thing. Question?
My question is, you did this for thermal electric storage.
Yeah.
You do it with chemical storage like batteries?
Yeah.
Is this the same conclusion?
I'm going to talk about that in a minute. So can you hold on to your question? Sure. Yeah, pretty much the same conclusions, yeah. Not quite, because, they're not quite the same, but they're similar. So this brings up to this, demand response to consumer, the business model. So apparently there's Guinness outside. Some guy, who's the guy who came in with the beer? Where is he? Oh, he was thrown out. So I showed 2 pints of beer, and what I say is, if I was to give my entire control of my entire electrical consumption to Hydro-Quebec or my own utility or whatever, they may be able to give you the price of 2 pints of beer a month for that privilege. They may. That's the type of numbers you're talking about for an individual. And they are, roughly speaking, if you look at the numbers across the world, that's approximately what it's worth. I don't know anyone in at least a modern society who would be willing to give control of electricity. Now they would guarantee your comfort and all the rest of it, but to be honest with you, 2 pints of beer, I know 15 Canadian dollars a month, it's nothing, it's zero. So in fact the demand side, the problem with it is, from the point of view of individual consumers, is the amount of money involved is very small. For large consumers who have huge loads and there's only one person involved and the transaction costs are low, these type of techniques do make sense, but for individuals it doesn't make a lot of sense. And when I hear people saying the business model is wrong, I always paraphrase, so you mean the subsidy isn't there? So I'll leave that one with you. If you look, there are definitely market barriers to demand side management, and there's different places in different parts of the world that it makes more sense than others. But in Quebec, I just had the answer. Storage. What are we doing storage heating for? So in Quebec, considering your cheap hydro, I don't see demand side management making much sense at all. And also it's a very flexible system, so I don't see a need. Now there are some very specialized services that demand side may be able to produce that hydro can't, but I won't talk about them here today. So there's no doubt about it though, that you do need to make sure that the market and the regulatory environment are such that it can thrive, because you'll always have people saying I can't do it because of regulations. So you should make the regulations such that they can do it, and then it's up to them to do it if they want to make money out of it. But if you have the regulations that stop them doing it, they can always rightfully say, the business model isn't right. So you should always try and make your regulations so that people can do whatever they want. So back trying to get to this gentleman's question about the chemical storage. So some of the work we've done on the integrated electricity, heat, the consumer, the house, etc. We looked at hybrid heating systems. This is where you have heat pumps, you have hybrid heating systems. You might have gas and a heat pump together, very expensive. You might have a heat pump and electric heating. And we're trying to look at sort of the flexibility that different forms of heating would give you. This is the whole idea that sometimes electricity is very cheap, so you can use it to heat, but sometimes it's not that cheap, so you can use gas instead, so it's hybrid. So out of that work, storage pops up as a valid thing to do, which is not surprising, because if you remember what Eisenhower said, if you make the problem bigger, these things start to evolve or emerge. Because if you make the problem bigger, you've got far more parameters to work with, and so solutions that are not in a smaller dimension will start to appear. So you have far less constraints. So let's look at dedicated storage into grids. I think this is what you were, is this the topic that you wanted to?
Well, I was more looking at the consumers.
Yeah.
Consumers cited
But you talking, so I was talking about thermal storage before that. I'm going to talk about dedicated storage. And what I mean by dedicated storage is electricity in, electricity out. Is that the topic you were talking about? Chemical. Yeah. So this is yeah. Okay. So this is what I'll deal with now. So dedicated storage, integrating dedicated storage. It is different than the previous one, because the previous one is I take electricity in, I store it in heat, but I reuse it in heat. So it's different. This is dedicated storage, which is electricity in, electricity out. So that's the difference. Okay. So I have a specific section on that. I knew he was coming, but I didn't know he was coming. So, island applications. So if you look at this gentleman here, his name is Nick Miller. Francois knows him well. Do you? Oh, okay. So Nick Miller's a GE engineer. He's a couple of hundred miles south of here in Schenectady. This is a battery. This is a lot of batteries in a small place here called, I can never pronounce its name, but you can read it yourself. And it's effective, I don't know physically whether it's an island, but electric it's an island, because you've got the Yukon in here. This is in the middle of nowhere, right? That's it. We'll just say it's in the middle of nowhere. Whether it's an island or not makes no difference. There's no electrical power transmission to it whatsoever, and why would there be? It's too far away. The oil or the diesel that they burn is probably, it's probably drilled here, sent by pipeline down, and sent by ship back up in a refined product or whatever. But anyway, it's incredibly expensive. So it turns out that batteries in these islands make sense, yeah, because the cost of energy is enormous, yeah, so it makes sense. And here's Quebec again with that nice thing. And in here it probably makes no sense, but I'm sure there's places out here. I'm really fascinated to go up here, but apparently there's nothing there, which is pretty obvious. But my wife actually proposed to me the night before she went back that we drive from here to St. John's. I'd say, that's why they have planes, my dear. 33 hours to drive there, so maybe not. So the simple fact of the matter is that batteries on small electric grids like this or up here make sense. So that's clear. We'll move on from there, get that out of the way. So I'm the chairman of the European Academy of Sciences, is all the national science academies in Europe. And I chair this group on a storage report, valuing dedicated storage and electricity grids, which is exactly what this gentleman wants to know. Now, the report is embargoed. I've been filmed, am I? Yeah, it's embargoed. I'll talk to you afterwards. It's embargoed till it's launched on the 19th of June. And I've also been involved in this study on the right, which is the Man Responsive Energy Storage Integration Study that was done by the Department of Energy of the US. And I was the scientific advisor on it, and that's been published. So that's the background of what I'm about to say. So if you look at storage, dedicated storage, electricity in, electricity out, and you look at it in the world today, this doesn't apply to Quebec, right, at all, really. In fact, you have 1 year's worth of storage in behind those dams, so it's a completely different thing. But if you look at electricity storage in the world today, 95% of it is pumped hydro storage, okay? Now, the other smaller amounts are growing, there's no doubt about it, particularly lithium-ion batteries, and I'll say something about it in a while. If you go to now, I have not done the scientific study on this, and I'm not going to try to publish this in a journal. I'm going to give you this. I did a piece of work for the IEA. There it is there. Oh, no, yeah. this piece of work here that I'll talk about in a minute. And the IEA asked me to do a bit of work on storage, and I asked them for all nuclear and all pumped storage built in the OECD countries, because the IEA is essentially the OECD. The IEA, of course, we all know is opposition to OPEC. That's what it should be called, OOPEC, opposition to OPEC. So I just asked them for the data, and I plotted it out here. Now, I'm not saying this is cause and effect, but this is the real data. So I didn't go into and dig any deeper. I'm not going to. I don't have the time. Well, maybe I do have the time sometime. But and I know that there's some engineers in the world who built these pumped hydro stations and built the nuclear stations, and they tell me that my conclusion is correct. And so just because two lines are correlated does not mean there's cause and effect. But basically, the story I'll tell you is this. When we were building lots of nuclear, your friends down in Toronto were building it, yeah, in Ontario. They're building lots of nuclear. And nuclear power is incredibly cheap at the margin, yeah? It's a capital expense. You've got lots of uranium here, don't you? Yeah? And this is where we should send it back to, but that's another discussion we'll have later. You and the Australians, we should send it back to you. But basically, it's a large capital cost infrastructure project, okay? And in the 1960s, right, you had nuclear at the base, and at the peak, what was the peak generation? It was oil, yeah? Now, it's no longer oil because of the oil crisis, etc. And also, we suddenly discovered that gas we were flaring off the oil fields could actually be somewhat useful, and we started using natural gas, and we started building CCGTs. So, if you look at it, what it basically was happening is, building nuclear, it turned out that the price spread between night and day was enormous in a lot of systems, because it was nuke at the base, which is virtually zero marginal cost, oil at the peak, which is very expensive. So the price spread was roughly 5 times. And therefore, the economics made sense to build these things. You take nuke at night, put it into a storage device, and replace oil during the day. So although they're very expensive to build, and the round-trip efficiency is around 70%, you end up with a situation where the economics make sense. And they built them. There's other reasons why they built them, and I'll talk about it in a few minutes as well. So then, all of a sudden, we have this situation here whereby, and then what happened is flattened out. Why? We stopped building nuclear, and gas was now at the peak, and gas is not as expensive as oil. And in fact, in a lot of systems now, it's not only is gas at the peak, but gas is also at the base sometimes. So you get this price spread that's not as big. So the whole economics of pumped hydro stations changed. Now, I haven't published this. I don't have the time. If someone else has the time, please go do the work. I'll act as a consultant. But I'm pretty sure that is why they were built. So if anyone asks you why there's so much pumped hydro in the world, this is probably the reason. And everyone I know, nobody I know disagrees with me. Then again, nobody I know disagrees with me anyway in anything. So that's a saying from that gentleman down south again. So if you look at this now, this is from, so the report's embargoed, but I'm the chairman, I can use the slides. So you can see that the cost of lithium ion is dropping dramatically, and that's one of the reasons why people are doing that. We're talking about the individuals, but I'm talking about the grid now here, it's a different thing. And look where it's going to, it's getting down, it might by 2030 make, and this is, we got all the best numbers in the world and we put them together. They're getting towards $100 euro per kilowatt hour, okay? This is a study done by the DOE a couple of years ago that I was involved with as well. And I won't go into huge detail, but storage, if you put more storage on the system, it eats its own market, yeah? Because, buy high, sell low. But if you buy more at low, the price goes up, yeah? And vice versa. So what does storage do? It kills its own market, yeah? So if you look at it, the more storage you put on, the value declines rapidly. These are different. I'll let you look at the slides later. But you can see the numbers, yeah? Yeah? None of them are over 100. So in fact, and this is on the Western Interconnection United States. So in fact, just by that alone, you can see, even by 2030, batteries still don't make sense. Okay? Does that answer your question?
Not quite. My challenge is that as long as it does service for the consumer, it may not pay off. But if it services the grid as well, then it pays off more than.
Now, I mean, in the interest of time and the interest of, well, when I sent the slides to Lauren, she said, there's too many slides, Mark. I do have other slides that show you instances where storage does make sense, particularly in ancillary services markets and regulation in some systems, yeah? And this is not that. So You have to take that. So there are niches where it does make sense, and I did actually have a slide like that. In fact, is it in my spare slides at the back? If it's not, you left them out. So it does make sense. In the PJM market, for example, at the moment, people can make money, for sure. But only ancillary services, not on arbitrage, correct? But if you look at it, and I also had another slide I took out, if you look at the Beacon Flywheel project that was in New York, and I went to the opening of that in 2011 because I know the guys, and they went out of business soon after that because when they started building it, the regulation price I think was $60 megawatt hour, and then it dropped to $6. So it's an incredibly volatile market regulation. So yes, it makes sense, but it's a very, I put it this way, if I was advising investors, it's not an area that I'd be investing in unless somebody had a subsidy. Anyway, so storage applications. So basically storage has lots of competitors because there's nothing it can do, direct dedicated storage, there's nothing dedicated storage can do on a grid that something else can't do just as well. It's got no unique proposition, yeah? Transmission lines have a unique proposition. Hydro, 3,000 kilometers north here or even further to Quebec, you got to have transmission, so it's pretty unique, yeah? Generation to turn water into electricity, pretty unique, yeah? But storage doesn't have anything unique about it. There's nothing it can do that something else can't do. And therefore, it's a hard sell. But in Ireland, we looked at it because in fact, we did a study for the Irish. How am I doing for time? Yeah, okay. So in Ireland, we did a study on renewables. I'll just take some more water. In Ireland, we did a study on renewables in 2006 and 7. And we looked at how much wind we could fit on the system. We did the economics, and then we did the technical stuff. And in terms of future scenarios, we didn't put any more storage in the system. None, zero. Because you could easily show, literally on the back of a cigarette packet with a pen, you could show the numbers. It just didn't make any sense. It's not that difficult to do the numbers on why storage doesn't make economic sense. Because it's a huge capital investment, and even though it's getting cheap, Mr. Musk may be making lithium-ion batteries cheap, but they're not as cheap as pumped storage in lots of places yet. So it's still very expensive. So you can do the numbers in the back of an envelope that show you it doesn't make any sense for the reasons I just said, and particularly if you have gas at both at the peak and the base. But there was a lot of people complaining to the government that said that guy O'Malley, blah, blah, he doesn't like storage. So we did the study with storage. And what we did is we said, when would it make sense? So we put enormous amounts of wind on the system. We placed the CCGT with a storage unit, and we asked ourselves, when does it come to the point where the net savings are positive? In other words, operationally and capital-wise, when do you make money, okay? And what it shows you, and look, I'm only showing you one graph in this paper. If you look at that paper with all different fuel costs, CO2 scenarios, they're not that much different, but I didn't want to clutter up. Basically, when we go to 50% energy from wind, now we're currently at 22, 23%. When we hit 50%, there is a business case for building another another piece of storage. However, what we didn't look what in this case, we compared this with a combined cycle gas turbine. What if we compared it with more transmission to the UK? Because we're exporting a lot there. What if we compared it to demand side management? What if we compared it, so we didn't compare it with anything else. So this is the best case scenario, okay? By far and away the best case scenario. The second point is, we don't actually have another site from an environmental point of view that people would let us use. So there's all sorts of reasons that we won't be building another pumped hydro station. There's other things I could say, but I'll move on in the interest of time. However, why did we build one? Because we do have one. We have a pumped hydro station in Ireland, yeah? It's 290 odd megawatts and runs for 6 hours, and that's a picture of it, yeah? And I've given it away, boys and toys, pumped storage in Ireland. We don't have nuclear. Why did we build it? Again, not a scientific fact, but your facts don't make any difference nowadays. My suspicion, and nobody has ever told me I'm wrong, is that when it was built was during the bad economic times, so it was a good old construction project to get plenty of people to work, which is good. And second of all, the engineers who ran that utility, which is completely and absolute monopoly, they love to build things. They like to build. Well, what's better than a bunch of engineers to tell me you're going to cut off the top of a mountain, build a lake in it, drill a hole through it, and put a generator 35 meters under the thing? It's a, I won't use the term, but I think wet dream is the usual term that's used. Yeah, the guys who just build it. So engineers do tend, and I'm pretty sure the same is true in Canada and the United States, engineers like to build stuff. And there was a bit of that. Now, it's a very useful device. I'm not saying it's not, but maybe 300 megawatts for 6 hours was more than we needed, because there's some very, very fast services you do need from it. Maybe 100 megawatts for 2 hours was a better build. It's probably overspec'd. We don't need it. And if we didn't have it, and in fact in 2011 we ran the whole system without it. So we have it. And in fairness, it was coal at the base and oil at the peak, which was a reasonable spread in price. So the economics, I'm sure they were able to do the sums. They didn't have Excel spreadsheets then, but they were able to do the numbers on it in such a way that it did make sense. But then again, anyone can do numbers that make sense provided the customer's paying, and you can force it through some regulated price. So I would suspect that a lot of them are built for this reason. It's the best engineering project of all time, a pumped hydro station. Civil engineers love it, mechanical engineers love it, electrical engineers love it, they all love it. I think it's great. Okay, so back to Quebec. So, this gentleman here is essentially the minister of the European Commission is a federation as well. Effectively, it has commissioners. Effectively, they're the same equivalent as ministers in a federal system, but our federal system wouldn't be as strong as the Canadian one or the US one. And this gentleman here is effectively the commissioner for energy, okay? And look what he said. Smart grids, balancing intermittent solar and wind energy with flexible power demand could do for Europe what shale gas has done for the United States, a senior European official said on Wednesday. He said it about 10 days after I had lunch with him. He did say it on the 1st of April, though. And I'm not certain whether it was before noon or not, but anyway, all I'll tell you is that that is a nonsensical statement. Shale gas in the United States has changed the entire planet's energy portfolio. It's just totally. It's changed the world environment and energy completely, totally and absolutely. There's no way that smart grids or all these things will come even close to it. So that's problem number one. You both have the Queen as your head of state, so I couldn't resist this. Why do you have the Queen as your head of state? What? Sorry? I'm an Irishman, remember? They're next door to us. We got rid of them. She's not our head of state. Huh? No. Anyway, so you both have the Queen as your head of state. I genuinely have no idea why a country has a head of state that's in another country. But anyway, that's for you guys to worry. Get those pills out during the winter and take more of them. Anyway, if you look at Australia and Canada, it's interesting. Now, culturally enriched by all nations except America. I have no idea what that means. Anyway, the reason I bring up Australia is I've brought it up once or twice before, but I don't want to bring up this man. Elon Musk is a South African. He's not Australian. But the South Australians had a blackout recently. The Australians and South Australia had a blackout. Long, torturous story, but nonetheless, the electricity system behaved exactly the way it was designed. Actually, from an engineering point of view, it got an A+. Well, maybe an A. There was one or two things, but it did very well. So yeah, the whole of South Australia without electricity, yeah, there was chaos, whatever. But from an engineering point of view, it did what it was supposed to do. So there was no failure in an engineering sense. Now, you can't tell that to politicians in particular, you can't tell it to people, but nonetheless, if you want an electricity system that's never going to fail, well then, 7 cents, you must be joking me, 700 cents a kilowatt hour, and then you still will fail. So, the problem with reliability is that when it goes wrong, it goes wrong. So it did nothing wrong. Anyway, chaos has reigned in Australia. There's another reason. The Australians have got something wrong with their gas. They're selling a lot of their gas to the Japanese through a compressed, or what's it called, natural, LNG, yeah. So they built a huge LNG plant and they're selling it on to the Asians at a good price. But they didn't quite work out their supply chain and they don't quite have enough for the locals. And so the locals can't get it, and therefore the price of gas in Australia is now higher than the LNG that they're selling to the Japanese. But that's just, again, it's a market problem. It's nothing to do with, someone screwed up. So energy in Australia is a very big topic at the moment. So between the price of gas and the South Australian, it's a big topic. Our friend Elon Musk, love or hate him, you have to give him one thing. Only person in the world that manages to get a prime minister of a country is his #1 salesman. Because Elon Musk gets online and says, he says he'll solve the energy crisis in South Australia in 100 days by using Tesla technology to supply as much as 100 megawatt hours of power. and he's now Twitter, whatever. I have no idea what Twitter is. I've never used it. I've never seen it. Well, I know what it is, but I've never been involved. Anyway, thanks, Elon. That's why I asked our clean energy finance agency to focus on storage, vital now with generation more distributed and variable. So Malcolm Turnbull in Australia is currently the #1 salesman for Elon Musk. You have to give it to Elon Musk. He pays him nothing, and yet he's selling his product. So my whole idea of these few slides is Quebec is doing just fine. Ignore these people. Conclusion. So integrated energy systems can help integrate variable renewables, improve. I didn't talk about resilience. It wasn't, and it's not an area I've done a lot of work in, but, if you integrate systems together, you get more sources. So resilience, increase efficiency. It's not only physical, but institutional, and also anthropological. That's my new word for the day. Planning these systems requires you to take all these, you can't just, say I'm going to integrate the system and then not, you must look at all these things together and how they interact, and you find some really nice things that go on and you find some bad things as well. Consumers are an enormous driver of this. They're probably the single biggest. I'm on the record as saying that we invest far too much research into engineering research in energy, and we should take a lot of it that's going to rubbish research, I'll use the word rubbish research, and give it to social scientists, because I think that's where we should invest our money. I think that's where we have most of the technology for these things. The problem is the consumer is going to do things that engineers, and I'll tell the story about my wife. Oh no, it's online. She's probably gone to bed, good. But my wife wanted a new car. I specified a car that was exactly correct for her requirements, and she says, Mark, I want a Volvo. So, my point is, engineers will tell you the answer. My wife wants a Volvo. So she has a Volvo. They're a lovely car, but it wouldn't be the car that I would have bought on the specifications that I was given. So the point is that consumers will do things that engineers and economists will, think are wrong, but that's what they'll do. And the balance has to be got between the two. I think the transport issue, I'm not an expert, but I would suspect that the biggest constraint on transport, I think there's a backstory. This man's going to give it to me over a glass of wine, aren't you? Probably. I suspect that the consumer constraints, how people use transport is probably a big issue in terms of electrifying transportation, I would assume. So I don't think it's a technical problem. There's probably some political problem as well I don't know about. But nonetheless, I think how they use it is very important. Quebec is incredibly lucky. Lots of renewables, not generally variable. You have wind as well, for sure. Very flexible. Transport looks like the main challenge in terms of your whole system. 2030 policies for Quebec. Efficiency is something I didn't deal with a lot, but efficiency, your attitude towards electricity here is, sure, just use it. Maybe, the incremental costs I hear of building a new hydro plant is pretty high, so efficiency is something you should concentrate on. I've done a little bit of that. Little need for many of the developments that are currently sexy. Yeah, you don't need to be, get on with it. You've got a great situation here, much better than most people. It's a classic case of every system is different. Like I said, I've said it before, every energy system is different, every solution is different. You've got a much different system than we have. You're probably very similar to Norway though. But remote areas are different. So again, although Quebec has a unique situation, your remote areas are completely different because they're not actually part of Quebec from an energy point. Well, sorry, in fact, I'm not talking about Quebec. I'm talking about the Lawrence Riverway or something like that. That's it. That is Quebec from a population point of view. And then beware of the snake oil salesman, like the gentleman I just saw before. I'm not saying Elon Musk is a snake oil salesman, but you might say that that's potentially true. But he's brilliant, you have to give it to him. And then anyone for lunch. So apparently my Prime Minister is in town tomorrow, or on Thursday, and he's having lunch with your Prime Minister. So after what I just said about snake oil salesmen, I'm going to have lunch with these two gentlemen on Thursday. I don't know whether I should or not. Is your Prime Minister any good? You don't have to answer that question. Our Prime Minister is on his way out. He's managed politically somehow to hold on. He is going, it's official, but he hasn't said the date, so you have to give it to him. He's pretty good at what he does. Well, sorry, he's pretty good as a politician. He's not pretty good at leading the country. That's a different thing. So then, acknowledgements, obviously the Irish-Canadian University Foundation, Trottier, Lauren in particular, and my colleagues for the use of their slides, and my students in particular for the use of their brains, because mine is I'm getting a bit old. And that's it. I've finished. Oh, look at that. Last slide. Okay, thank you. Let's see if I had those slides. I think, do I have? No, I don't have. Yeah, I don't have that other slide I was talking about in the back slides. Okay. Any questions? Or have I done all the questions, have I? Yes, sir.
We have an internal study by McKinsey company which shows that in Quebec we will have grid parity for solar up in maybe 2025, and we are very scared about that because the projections are that we may have 10% penetration of residential solar in Quebec, I will say by the term of that energy plan you have shown. So what is your opinion about that? Is it, because after all, we are not in control. The consumer is in control.
Yeah.
And is it likely or not?
Well, I'm a systems person. I don't deal, okay, I have to know about all the technologies, but I'm technology neutral, okay? My job is, as a systems person, is to sort of put them together, okay? So that's the first thing. So I'm not wedded to any technology, good, bad, or indifferent. I just need to know its characteristics, and I'll tell you how they behave. So I don't have any particular technology that I do or do not promote. I will say one thing against myself. I do not believe that ocean energy, wave energy, will ever work, but that's just a particular pet hate of mine because the Irish government invested, I might have been filmed, am I? Anyway, let's just say that somebody I know invested an enormous amount of money in it, and it was a bad use of money, so I'm a bit upset about it. But anyway, so I'm not tied. If what you say is true, let's assume that solar gets incredibly cheap, yeah? That's the assumption you're making, and whether it does or not, I don't know. It is definitely getting cheaper. Somehow I suspect by 2025, being grid parity in Quebec is a little bit of a stretch, but nonetheless, let's say it reaches grid parity. The simple fact of the matter is, as I understand it in Quebec, Hydro-Quebec is owned by the government, yeah? And decisions were made, and so you have a situation where decisions are made. Now, if there was investors involved and made decisions, then if lots of solar came along and they went out of business, then so be it. There's a tendency in electricity, however, for the market not to be allowed to work, because electricity is sometimes deemed not to be really a commercial product. It's sometimes deemed to be, somebody used the word the other day, it's almost like a human right. Electricity to some extent is becoming a human right. Water is a human right, isn't it? My understanding is under United Nations rules, water is a human right, yeah? So selling bottles of water is a little bit odd, but nonetheless, it's a human right. So I think the day is coming where electricity might actually become a human right. And therefore, and that's, my point is, electricity is not like any other product you know. It's become so important to how we live our lives that it's not just like buying bananas or apples or in fact, the only market, pure market in the world that I know is the one in heroin on the streets of big cities, because there is no regulation at all, and it's a pure market. So most other markets have some sort of interference, and I think electricity is hugely interfered with because it's so fundamental to life. So I think if solar gets really cheap, lots of people put in their roofs, there could be lots of stranded assets, lots of problems, but nonetheless, the society made a decision to build them, someone has to pay. I mean, I think it's great, people think it's great in Quebec when they have electricity, and it's great, but somebody built it, somebody invested money in it, and all of a sudden you have to take your responsibilities, and your responsibility are that you're part of a society that made that investment. You may not agree with it, but it happened. So it's a classic case, though, when things go wrong, everybody runs for the door and leaves someone else to pick up the bill. So if PV gets really cheap, more will be installed. But then if you end up in a situation where Quebec, you have huge amounts of extra energy, you should build more transmission to New York because the prices are very good down there. The problem with that, though, is what? If you build lots of transmission to New York, eventually you'll get New York prices here, and that is a consequence of building the transmission. And if you think you can avoid that, you can't. So do you want the prices in New York? Hands up. No one. So it's a complicated question. Yes, sir. It's about storage, I bet you.
You bet. My name is Maurice Malka. I'm with TSI-ECHO. So I'm trying to zoom on the value of distributed storage, and in particularly as an energy resource, meaning that you can cycle that battery to the point where it can play multi-services.
Yep.
And my suspicion is it's as valuable in Quebec, given even the low price, because relative to what? We pay what we have to pay. We've heavily invested in Quebec to own this utility. Ontario did the opposite, and now they're buying from Quebec because they needed a cheaper price for their electricity. As a matter of fact, this is important to know, that Hydro-Quebec is also selling a lot of energy to the US. Even though they cannot build the transmission line, they're part of the trading system. And of course, they're selling their energy as high as they can, and they do ask for curtailment, particularly during the winter months, where they would love to have more available energy, but they never let their consumers without service. So it's important to understand that the price of the market depends very much on what you can get out of your own market and export. So my concern is the following. In most of the studies you've referred to, none of them address the problem of transmission, distribution. You mentioned the word resiliency, but no seamlessly indication of service availability, which is, you know, when you hear 99.98%, you say, wow, impressive, right? However, it works out to be 15 hours downtime cumulative a year, which is very difficult to swallow, particularly if you need a backup diesel generator and you pay for that fuel. So the question that I'm going to raise to you is any of your studies taking into account what the ISOs are doing in the States, in trying to regionally at least provide compensation for those who provide curtailment or other more real-time services, which in most cases involve, when they're clean, the use of cycling of batteries?
Okay, so first of all, I've never done a study in Canada or in Quebec, so I've never done the numbers, right? I'm giving you the numbers of studies I do know about and have done, okay? So that's the first thing. But looking at Quebec and looking at what I see a system that's got an enormous hydro resource that's enormously flexible, right? It is incredibly flexible, right? And therefore, the value that's put on a lot of the services you just said is extremely small. Now, if you go to New York or, down at Boston or whatever, they do not have cheap hydro. They have expensive gas. They have a huge amount of transmission, a much different system, and the value on these services is much higher. So the fundamental value of the services, as I understand in Quebec, is very small. So ancillary services, that's what you're talking about to some extent. It's extremely small in Hydro-Quebec as far as I can see. I'm only looking at numbers I've seen. I haven't delved into it. I could be wrong. So that's the first thing. I do not believe the value is here in this market at all. Second of all, in terms of energy is fundamentally so cheap here as well. Arbitrage, arbitrage means nothing here. What are you doing? You're arbitraging water with water. There's no price spread at all. So therefore, I really don't see how storage makes sense in Quebec. Now, if you then go and say you're going to sell services to New York, then fine. But you have this problem that you don't have enough transmission to it. So, and resilience, we talk about resilience for a minute. So there's no doubt about it that, if you do want, you had your ice storm here a few years ago, yeah? And you had big problems, et cetera, and all the rest of it, and that's fine. And, if you had batteries, it'd be great. But, it's the old story is that if you want to, you'll only know if it works if it happens again. That's the first problem. And the second problem is you don't need the whole system to be resilient. You just need a few little pockets, hospitals, etc. You don't want everyone to be resilient. If everyone wants to be resilient, let them pay the money. So let me give you an example. There is one place I know in the world where there is somebody who's making their system completely resilient, right? It's on the island of, is it Lanai in Hawaii? Anyway, the man who owns it is the same man who owns Oracle, who's called, what's his name? Sorry? Larry Ellison. So Larry Ellison can probably afford a few, toys, etc. So you get situations where people do it, but it's the US military, yeah, they want to be resilient. The US military, I don't know, apparently a pencil in the US military costs $10 because it's so highly spec'd, So they are very special cases. But for you and me, ice storm comes, wrap up, keep yourself warm, wait till the good guys come. Because it's very expensive. And people, do you ever see people invest in the future, do you? Most people don't. Most people like to live for the here and now. And I know one thing for sure, I want to live the here and now because I have no idea whether I'll be here when the next ice storm comes. That might seem like a flippant answer, but there's no doubt about it for resilience for systems like military, very high value sites, very important sites. Batteries do make sense. It's just a bit like, those batteries in Alaska. So they definitely make sense. So batteries do have huge potential in very niche applications in ancillary services markets in areas that are highly constrained and the price ancillary services are large, or in island situations, be that in northern Quebec or in a situation whereby you want to make sure electricity or energy source is still functioning in the case of an ice storm or whatever. But generally speaking, large-scale deployment of them. I mean, why would you deploy batteries when it's an additional capital cost, right, that you don't have to make, and it's not a small one, and the round-trip efficiency from an energy point of view is at best 70%. So you get a situation, they've got a fundamental, as a product, I think batteries are going to grow because they're getting cheaper, there are going to be more uses of them, but it's not going to be this takeoff point. Unless somebody comes up and divides the cost by 5, is the type of number you're going to have to do, by 3 or 4 or 5. If that happens, then they might take off. But fundamentally, batteries have a problem. They're an additional capital investment, and they cause inefficiencies. So I wouldn't think I'll put it this way, it's not going to be like, it's not going to be like the boom in text messaging and having the telecoms business. It's not going to become pervasive. But it's certainly a good business to be in. There's certainly money to be made, but it's not huge.
Again, my analogy will be simple. I wouldn't live today if I have a choice between my desktop computer and my laptop. I prefer my laptop.
Yeah.
Why? Because it has this uninterruptible capability which gives me up to 2 hours of reserves, which is kind of handy, protects me against whatever Hydro-Quebec may have as a problem. So there are reasons that may not be just economical why people do things, as you illustrated yourself. And this is why I believe Quebec has a great potential not only to make batteries, but all the power electronics, and sell them to the rest of the world, maybe with a recipe as how to be more cost effective.
So on your laptop, right, when it's on your lap, it gets hot, doesn't it? Yeah? And that is the actual energy itself, because it's mainly waste heat, okay? If you know your Carver Mead, you read your textbooks, you see it's mainly heat, okay? Do you think that the laptop is going to keep this warm room? Not a chance. I think people misunderstand. These things are not energy storage devices. They're power devices, because the amount of energy stored is so insignificant as not to be. They really are. They're tiny. If you put it another way, in that pumped hydro station that we have in Ireland, it is a top of a mountain cut off, right? It's a huge engineering project. How much energy is stored in it relative to the amount of energy we use? 20 minutes. That's it. So it's an enormous $1 billion infrastructure project on a small system. Our system is tiny, and yet it'll only last, from an energy point of view, 20 minutes. Another calculation I've asked my students to do is how many AA batteries does it take to have the same amount of energy? And the simple fact of the matter is there isn't enough to be bought in the world market over a period of 2 weeks. So batteries are tiny amounts of energy. They're very useful, but they're not going to keep you warm.
Well, they got to be used wisely for situations where they actually render a bigger service than their cost.
Yeah, but the single biggest use of energy in this place here is heat during the winter, correct? And it's the single most important use of it, yeah? And therefore, from a fundamental resilience point of view, heat is what it's all about. And if you look at the amount of energy that's required, there isn't enough batteries ever made. You know what I mean? The scales are just totally different. And that's what I think people have to understand. Scale. Yeah, as I tell my students, engineering is the art of approximation, and one of the things an engineer should always do first of all, before they attempt any project, be it a simple 2-hour project or 2-year, $20 million project, is get your pen and paper out, do a few calculations, and get the scales right, see what you're dealing with. And if you deal with it, the amount of energy that you use to heat in this province is astronomically large, and the amount of batteries that it would take is just, in fact, there you go. Francois, set it on an exam paper. How many batteries to heat Quebec? And, you know, there probably hasn't been enough batteries made in the world over all time to heat Quebec for a month. I don't know, but something like that. So batteries are used for you know, laptops, cars, mobile phones, but in terms of energy, it's tiny. In fact, somebody told me here you could put the entire, or 1 million cars in Quebec, and it would just be a dent on the Quebec. Isn't that right? I think somebody told me the other day you could put 1 million cars in Quebec, electric cars, and the Hydro-Quebec system wouldn't, well, it would notice it, but only minorly, just showing you the whole impact that, you know, the battery electric vehicles, people think there's a lot of energy. 1 million cars, Hydro-Quebec say almost irrelevant, because most of their energy is going to heat you in the middle of this city during the winter. And that's another thing you should do here, is you build your houses a bit better, because I've noticed from, yeah, I'm renting a very nice apartment, but I mean, in Ireland it wouldn't, your heat is so cheap, you're building your houses at a very low standard, which maybe you shouldn't do. You should save your energy and sell it to the Americans for big bucks. That's what I would do. But, huh?
That's really the business case for storage in Quebec, to store and sell to the United States.
No. The amount of money you make off the Americans wouldn't pay for the storage.
It's actually to put the battery in the States and ship our cheap energy and resell it at peak time.
Because the amount of money you spend on the battery, you never get it back from the Americans. Never. Never in a million years.
Well, at the rate at which the batteries are coming down.
But you saw my numbers.
No, well, those numbers are projections.
Sorry?
Yeah, arbitrage of power is bigger than arbitrage of energy. As long as you concentrate on arbitrage of energy, you don't see the difference. But a kilowatt hour is a kilowatt during an hour. And therefore, you have a lot of peaks that you can absorb with that battery. And that's where the arbitrage is. You don't resell kilowatt hours or megawatt hours. You resell peak demand. Yeah,
which is not, and that is capacity, and I just showed you, capacity. You could, storage could have some chance in the capacity markets, and I think in PJM they do have some chance. But generally speaking, look, you do the numbers, no matter where you do the numbers, they're hard to make the numbers up. Do you disagree with these numbers, though?
Yes, because right here in Quebec, I can show you peak shaving is 30% savings on the big bill, even though it's cheap. So 30% is nothing an owner would leave on the table.
But are you willing to pay 200 euros, say 250 Canadian dollars per kilowatt hour, and you make money on it?
It pays its way. Yeah, it's cost effective, and the payback is less than 4 years, which means anybody can do it.
Yeah, well then do it.
Well, it's being done, but I'm saying it's much more cost effective to do it where the price of energy is much higher.
Okay.
That's the point. Well, thank you very much.
Okay.
I wondered if you'd had occasion to sort of tease out your research or implications of the research on variable renewables for the developing world, like Africa, that sort of thing.
Yeah. So I haven't done any work in detail on myself, but I'm very interested in it personally. If you go to the developing world, these very small systems make an enormous amount of sense, because the value that people put on it, and the value that you put on, you people have no value on the incremental value. You waste energy all the time. But if you want to keep medicine cold in an African village, the value is enormous. And therefore in those systems, some of these micro systems make a huge amount of sense. So, but the problem with everything is the value of the first few kilowatts is enormous, and after that it declines. And therefore the idea that you can scale these up doesn't work. But to keep medicine, well actually, people walk 10 kilometers to charge their mobile phone. So the value they put on it is enormous. So in those cases, these PV and battery systems do make sense for sure. And in fact, there's one of the other, somebody told me, and it's a true story I was told by someone that said one of the values is to have lights around is to stop women from being raped at night, which is, you know, it's not a pleasant thing to say, but there's huge value in that. So there is value to be got. But they're very niche as well. And if you want to develop them into full, you know, modern economies, the value people will have on energy will decline, and therefore the cost will not matter. So very small amounts of energy people value hugely, and therefore these solutions make sense. Does that answer your question? We're done. Good. How about standing? I'm going to sit down.
Of course. Well, so that was excellent talk, Mark. Just a few comments. On May 17th, we have our next TISET event, public event, a talk on green chemicals. So if you're interested, please look up our website. And I'd just like to thank everybody again for coming to this event, and Mark for the excellent talk. He's going to be around with us for a while longer, so we're going to learn more from him. And last but not the least, we've got a cocktail reception that's 2 floors up in the billiards room, and so maybe they're serving Guinness, and so I invite you all to join us there. Thank you.